Hi, my name is Andrew, and today I'm going to be talking about trimming raw sequencing reads. In this RDMbite, you will learn which are the key FastQC metrics needed to inform read manipulation, including both raw read trimming and adapter removal, and see how trimming can drastically improve a dataset. This video follows on from the FastQC Explainer RDMbite. If you're unsure what FastQC can tell you about sequencing data, check out that introduction and come right back. As we know, FastQC produces summaries for many different QC features. Here, we're going to ignore potential technical problems within the flow cell, and instead focus on three key areas: base quality, GC content, and overrepresentation levels. Per base sequence quality looks at the average quality at each read position throughout the entire dataset. The boxplot histogram here is a near-perfect example of improvements in sequencing technologies. This dataset is from 2013 and shows 3' read deterioration. Trimming to a quality threshold is needed here to remove parts of reads which have low quality. Whilst the values in this example look good, the strange dip in the middle is consistent with adapter retention. This is when the priming adapters also get sequenced, in this case when short sequencing fragments or adapter dimers are included in the sequencing run. This can happen if one starting library has much lower starting material than others prepared at the same time. Reads with such poor scores as seen here are unlikely salvageable, as a Phred score of 4 reflects a 2 in 5 chance the base is incorrect. This plot raises the important point: are your data what you thought they were? Always have checks in place. GC content should follow the modeled distribution well, but many adapters have a 50% GC content, so distributions can appear very skewed. Again, the ideal is to have no overrepresented sequences, either by recognizing and removing specific headers or compiling a list of all possible adapters listed on the Illumina pages. Interestingly, biologically relevant groupings can appear technical at first. In this case, BK virus transcripts are massively elevated in this sequencing data, producing seemingly overrepresented sequences. It's always good to run any no-hit sequence back in BLAST before removing anything. So, we have two scenarios, one with some adapters and quality issues at the 3' end of sequence reads, and another with good data but high adapter levels. There are many tools available for trimming reads, including the popular TrimGalore and Trim-O-Matic. The most basic filtering strategy is on quality, and a value of 20, 1 in 100 chance of error, is commonly used. Strict quality thresholds are often conservative and result in large reductions in read length. However, a sliding window threshold approach, typically of 4 or 5 bases, allows trimming only when the read has become of consistently poor quality. After end trimming, reads are only retained if they are over a certain minimum length. Often this is a rule of thumb 50 bases, but the threshold simply needs to be longer than the minimum sequence match needed for alignment, typically 25 to 35 bases. Importantly, paired end reads are considered as a single dataset by trimming tools, so users must be aware of what happens if quality significantly differs between pairs, particularly if one read is removed and the other kept, creating unpaired reads. Trimming programs often create 4 files: paired read 1, paired read 2, unpaired read 1, and unpaired read 2. Some aligners can work with this directly, others need data back into concatenated and sorted FASTQ files. Users also need to provide the trimming tool with a list of adapter and generally overrepresented sequences. By performing trimming, example dataset 1 has improved the quality distribution of the data to largely be within the highest confidence green section, with GC percentage unchanged and no overrepresented sequences. Trimming adapters from reads with poor quality centers was also successful in example 2. Removing all overrepresented sequencing, normalizing the GC distribution, and removing low-quality sequences all improve sample QC. The key thing now is to assess how successful trimming was. FastQC can be used again to check improvements in QC. It is important to consider what proportion of reads and total covered sequence is lost during trimming, as it may be worth relaxing thresholds to increase read numbers to provide sufficient statistical power for downstream analyses. That concludes our look at sequence read trimming. Take a look at the links associated with this video for more information, and more RDM bytes in this area.